Ahoy RobotX community. We are team SINGABOAT-VRX from Nanyang Technological University, Singapore. Our team had participated in the Virtual RobotX Competition 2022 and we bagged the international third prize along with many other special awards. We have configured our VAMV with 3 thrusters in T configuration and a comprehensive sensor suite comprising of a GPS receiver, an inertial measurement unit, an RGB camera, a 3D LiDAR, and an acoustic finger locator. Apart from these, the autonomous surface vehicle also hosts a small cannon to deliver projectile payloads. We employ our ASV to address 6 different tasks of the competition in order of increasing complexity pertaining to different aspects of autonomy including perception, planning as well as control. The first task is that of autonomous station keeping, wherein the ASV is initialized in a drifted state. It has to localize itself within the environment and then drive towards the goal and maintain its course thereafter, taking into account environmental disturbances such as waves and wind. We have implemented a cascaded control architecture which acts in 2 stages. First, the ASV is driven straight towards its goal. Here, the longitudinal linear velocity of the ASV is controlled by a proportional controller which acts on the distance between ASV's current position and the goal position. The angular velocity of the ASV is controlled by a PID controller acting on the heading error between ASV's current orientation and the orientation of line segment joining ASV's current position with the goal position. Once the ASV reaches near its goal, the control architecture switches to the second stage. Here, the linear velocities in longitudinal and lateral directions and the angular velocity of the ASV are controlled independently using 3 decoupled PID controllers, which collectively minimize the pose error of the ASV with respect to its goal. This allows faster locomotion and robust disturbance rejection in each degree of freedom. Finally, and this is common for all other motion control tasks as well, an inverse kinematics module is implemented to map the velocity commands generated by the controller represented in Cartesian space to the thruster commands represented in joint space of the ASV. The second task is that of autonomous wayfinding, wherein the ASV has to track a series of waypoints while localizing itself within the environment. The controller is meant to track those of the ASV with respect to each waypoint while countering environmental disturbances. We have implemented the same cascaded control architecture as described in the station keeping task with 2 modifications. Firstly, we have implemented a waypoint indexing mechanism which ensures that the ASV has tracked all the specified waypoints and keeps looping through them until the task ends. This allows the ASV to minimize errors in subsequent trials in case it couldn't do so earlier due to reasons like environmental disturbances or inconvenient angle of approach towards a particular waypoint. Secondly, instead of station keeping very accurately, the ASV is considered to have reached a particular waypoint if its collective pose error is less than a certain threshold, after which it is commanded to drive towards the next waypoint. This eliminates the bottleneck causing the ASV to get stuck at a particular waypoint and failing to track the remainder. The third task specifically targets the perception module, wherein the ASV has to employ its exteroceptive sensors like camera and LiDAR to detect, characterize and localize various objects in the scene. The perception pipeline has to be robust enough to deal with uncertainties pertaining to vehicle motion due to waves and wind, sensor noise and environmental variations such as lighting and fog. We have formulated a sensor fusion algorithm that fuses LiDAR and camera data to accurately detect, classify and localize various types of buoys in the scene. The system detects point cloud clusters using density-based clustering algorithm and associates them with the corresponding RGB contour detections while resolving any inconsistencies in either sensor measurements. This way, both the sensors collectively detect the buoys by matching respective detections, camera classifies them based on their shape and color, and LiDAR localizes them based on the ranging measurements of the respective point cloud clusters. The fourth task is that of semantic navigation in an augmented wildlife scenario populated with virtual markers representing three different types of wildlife: platypus, turtle, and crocodile. The ASV has to detect, identify, and localize these wildlife elements and plan and execute a trajectory that circles clockwise around the platypus markers, counterclockwise around the turtle markers, and avoids the crocodile markers by maintaining a safe distance from them. We have implemented a path planning algorithm which fits bounding circles to each animal and plans tangential paths to approach or circumvent them. Once the ASV reaches near the tangent point of a safe animal, that is platypus or turtle, the planner plans a circular path around it, clockwise for platypus and counterclockwise for turtle. This path is then tracked by a proportional controller which acts on pose error with respect to the planned path expressed in polar coordinates. We have also implemented a circle tracking algorithm to check the circling progress of the ASV around a particular animal. This way, the ASV is assured to have completely circled a particular animal before moving on towards the next one. The fifth task involves channel navigation, obstacle avoidance, acoustic beacon localization, and station keeping. The ASV has to first navigate across a channel defined by color-coded marker buoys. After traversing the channel, the ASV enters into an obstacle field comprising of black and orange round buoys. It has to localize and drive towards an underwater black box containing an acoustic finger without colliding with any of the obstacles. Once the distance to the acoustic finger is minimized, the ASV has to maintain its position over it through station keeping. We have implemented a finite state machine which shifts its states automatically by detecting different events of this task. For channel navigation, we have implemented a gate detection algorithm which makes use of the semantic buoy detection algorithm from the scene perception task and adds a few measurement checks to detect different types of gates of the channel. As a precautionary measure, we have set up a timer for detecting each gate, after which the ASV is considered to be stuck in the channel and is commanded to directly locate the finger, navigate towards it while avoiding any obstacles in the way, and hold its position over it. For finger localization, we transform the range-bearing measurements represented in ASV's local frame from the acoustic finger locator into the corresponding positional coordinates represented in the global frame, which are then passed as the commanded goal position for the ASV. For obstacle detection, we have used the same semantic buoy detection algorithm from the scene perception task, and for collision avoidance, we have implemented a potential field algorithm which repels the ASV away from any obstacles detected in its close vicinity. This way, the ASV is not spooked by the obstacles that are too far from it, and hence not really harmful at the moment. Throughout this phase, the ASV makes use of Vibin's path planning algorithm and tracks the planned path using a decoupled control architecture. A PD controller minimizes the heading error between ASV's current orientation and orientation of line segment joining ASV's current position with the goal position by regulating its angular velocity, and an adaptive proportional controller regulates its longitudinal linear velocity based on distance to goal and shifts the velocity profile band based on the detected obstacles. Finally, once the distance to the acoustic finger is minimized, the ASV maintains its position over it by employing the same control architecture as described in the station keeping task. The sixth task is called Scan Dock Deliver, wherein the ASV has to first detect the light buoy and scan the light sequence to determine the appropriate bay for docking. It has to then approach the docking bays, identify the correct one, and execute a safe and controlled docking maneuver. The ASV has to then launch projectile payloads through one of the two holes in the placard at the head of the correct docking bay, and finally exit the dock safely. For scanning the color code on the light buoy, we have implemented a computer vision algorithm that first detects the vertical rectangular display of the light buoy based on its contours and width to height aspect ratio, and then scans the color sequence starting when the display turns off, that is black color. This color sequence is then decoded to determine color and shape of the target docking bay placard symbol. As a precautionary measure, we have set up a check to validate the decoded color sequence, upon the failure of which the ASV is commanded to dock to a random docking bay. Once the color sequence has been determined, we use LiDAR data to detect and locate the docking bays, and then try to detect the color using HSV color thresholding and shape using contour vertex thresholding of each placard symbol using the camera feed. Next, the detected placard symbols, that is colors and shapes, are matched with the color sequence decoded earlier to determine the target docking bay. Again, as a precautionary measure, we have set up a check to detect if none of the placard symbols match the decoded color sequence, upon which the ASV is commanded to dock to a random docking bay. Once the target docking bay is confirmed, the ASV plans a Dubin's path to the dock and tracks it using a decoupled control architecture. A PD controller minimizes the heading error between ASV's current orientation and orientation of line segment joining the ASV's current position with the goal position by regulating its angular velocity, and a proportional controller regulates its longitudinal linear velocity based on distance to goal. Once the ASV reaches near the dock, it rescans the docking bays to double check their poses and placard symbols. It then approaches the target docking bay by making use of a proportional controller which acts on the pose error with respect to the planned path expressed in polar coordinates. Once the ASV reaches near the target docking bay, it halts for a few moments and proceeds further with caution, halting after a threshold distance each time to ensure a safe and steady docking maneuver. Once the ASV has docked successfully, it positions and aligns itself to deliver the projectile payloads through one of the two holes in the docking bay placard, and then shoots the projectiles one after the other. Finally, the ASV safely exits the docking bay by driving in reverse direction.